welcome to Klein's Calculus. We're going to look at limits again. This is lesson 2.2, so we're going to look at the limits involving infinity as you move to the right into positive infinity, to the left as you move to the negative infinity. So we're looking at limits. We'll look at the sandwich theorem again. We talked about it in the last slide. We're going to look at infinite limits as x approaches some value, vertical asymptotes. We'll look at behavior models, which are horizontal asymptotes, and we'll try to visualize the limits from the functions as x approaches positive and negative infinity. I'll show you a nice, easy trick for doing that. First thing we want to look at is this idea of an asymptote. We know a line is a horizontal asymptote if either the limit as x approaches infinity of f of x equals some number, some horizontal line, y value, or as it approaches negative infinity, it equals some y value. So it doesn't mean it's a horizontal function. That just means as it approaches infinity from either the right or the left, you get a constant y value. So it doesn't have to be from both ways. And a function can have more than one asymptote. We'll look at a case where you see two of them, one for positive infinity, one for negative. And we know line x equals a is a vertical asymptote if the limit as x approaches a to the right or x approaches a to the left is either positive or negative infinity. So you can get a vertical asymptote if you have one of three situations. Either, let's call this a, maybe from the right it goes down and from the left it goes down. So same. If we call this a over here, maybe from the right it goes up, or left it goes up, and the right it goes up. So that's approaching positive infinity, and this is a vertical asymptote. And sometimes you'll get where it's coming down here and coming up here. So you could have it to where it approaches negative infinity one way and positive the other, or it can go towards positive or towards negative. So three different ways to get asymptotes. We'll take a little peek. I've got a function over here. We're going to look at 2x plus 3 divided by x minus 1. Okay? And I've just got my window, negative 10 to 10 in both directions. And as we look at this, we can see a couple things happening. I see a vertical asymptote right in here. So I know that's going on because this is headed towards positive infinity and this is headed towards negative infinity. And I also see a couple horizontal asymptotes developing to negative infinity to positive. And we're going to look at that sort of thing in great detail. So notice here, and this appears to be lower than this one. But how do you check that out? One way is to look at your table. I'm going to go to the table set and table start, and I'm going to say, let's ask my independent variable. So I'm seeing here, this looks to be at about 1 or 2, my vertical asymptote. So that one I'm just going to actually calculate a value right here on the graph. If I put in x equals 2, I get y equals 7. If I put in x equals 1, notice I get y equals nothing. So I know my vertical asymptote is at x equals 1. Okay? Now to find my horizontal asymptotes, let's go to the table and we're going to ask. And we're going to ask to find out our, as it tends to infinity, let's ask for very large values. Here's 1,000 and I see it's 2.005. Here's 500,000, 50,000, 2.0001. So it's settling in, and we're going to have the limit as x approaches infinity to the right. It's going to be about 2. That's going to be a horizontal asymptote to the right. Now let's look at the negative numbers. Negative 20,000 or 200,000. And you see there we've got a 2 also. If you get the bigger numbers right away, you see. But let's do it again. Let's go negative 50,000. 1.999. So you can see these are all settling into 2. So there is going to be one horizontal asymptote to this function, and it's going to be y equals 2. So you can find them graphically that way. Now, that's kind of what we just looked at. We'll look at one more here. Let's look at the function. We're going to turn that one off and this one on. So now we're going to look at x divided by the square root of x squared plus 1. And we look again, negative 10 to 10, and you can see this sort of thing. We don't have a vertical asymptote, but graphically you can see it looks like it's going to settle into negative 1, and it's going to settle in at 1 here. If we look at our table, we look at 1,000, it's 1. We look at 50,000, it's 1. So positive infinity, the limit's going to be 1. Negative infinity, the limit's going to be negative 1. So just as we suspected graphically. So ways to find horizontal asymptotes. Okay, now let's look at our sandwich theorem a minute. We've got a nice, remember our friend, the sine of x divided by x. We want to look and see what's happening to that as it heads to infinity. We'll look at it graphically, and then we're going to look at the table. So we can see, if we come over here, if we go negative 10 to 10 in both directions, this is what we see. So, and you know that the sine of x is going to oscillate. So let's look at our numbers here. And we can see, you know, when we've got e to the negative anything, we're looking at very, very small numbers. It's 10 to the a negative power. So these numbers are very, very close to 0. So you're thinking it's oscillating back and forth, but it's getting closer and closer to 0. Our limit as x approaches infinity. Now, we can use our sandwich theorem here. We can take this, and we know that the negative 1 is less than or equal to the sine of x, which is less than or equal to 1. We know that because those are just the limits of the sine of x. So now we've got the sine of x over x, and we have our 1, negative 1 and 1. And, excuse me, I can, if I take this and the first thing I want to do, this is divided by x to get from here to here. Just divide everything by x, and now I've got my target function. Okay? Now I can find the limit of each of these. The limit as x approaches infinity, the limit as x approaches infinity, the limit as x approaches infinity. So if you put a really big number here, you've got negative 1 over something getting bigger and bigger and bigger, you're going to end up with 0. The bigger the denominator gets, the smaller the fraction. Same thing's going to happen over here. So I know the limit as x approaches infinity of sine of x over x is between 0 and 0. So I can say that the limit as x approaches infinity of the sine of x over x equals 0 by the sandwich theorem. All you've got to do is write this out. Step 1, divide everything by x. Start with a known relationship. Divide everything by x. Take the limit of what you can. And if they're the same, the limit of this must also be that. So there's our sandwich theorem revisited, and we saw it graphically just a minute ago. About limits, we talked about this in the last slide. They're all numbers. So you can add them, subtract them, multiply by a constant, divide them, raise them to a power, unless they're infinity or negative infinity, in which case you can say infinity and negative infinity. And that's not really the limit, that's just the behavior of the function. But it's nice to be able to give that so I know that you know what's going on with it. Okay? Looking at those rules, if I saw something like this, I just have one number in the denominator, so if I want to find this limit, I don't have to do it graphically. I can split it up. This is going to be our sum theorem. And this is the same as the limit as x approaches infinity of 5x over x plus the limit as x approaches infinity of the sine of x over x. And you can find both of these. Well, first thing I'm going to do is I'm going to simplify that. That's just 5. X over x is 1. It doesn't matter what number it is. So now I've got the limit as x approaches infinity of the number 5. It's just going to be 5. And the limit as x approaches infinity of the sine of x over x, which we just determined to be 0. So that means the limit of all of this equals 5. And if you graph it, you can verify that. Okay, just look in your table of really large numbers. Okay, so just break it down to smaller functions if you can. Now, what if we want to find a vertical asymptote? We want to find, let's find the vertical asymptotes of f of x equals 1 over x squared. And we're going to start with that. We'll look at it, negative 10 to 10. And we kind of know, we know what's going on, right? It's going to be, vertical asymptotes are always where the denominator is undefined. And it's undefined where x equals 0. So we know, and we'll just write that down, vertical asymptotes, when the denominator is undefined. So when x squared equals 0, or when x equals 0, that's where we're going to find our vertical asymptotes. No matter how big, ugly, funny that denominator is, you just set it equal to 0. That's how you find your vertical asymptotes. Now to find the behavior, to look at the behavior to the left and the right, plug in very small numbers to the left and the right of 0. Or if you've got a graph, look at this, and I would say it's tending, f of x is tending towards positive infinity, both to the left and the right. So we can say the limit as x approaches 0 from the left of f of x equals positive infinity. We can say the limit as x approaches 0 from the right of f of x equals positive infinity. And if both of those things are true, from the left and the right, same, then we can say the limit as x approaches 0 of f of x equals positive infinity. There's a vertical asymptote there, but the function's behavior is going the same way from both directions, okay? Now, let's look at this. Trig is always more fun. Let's say you've got f of x equals the tangent of x. Now we know, we think about, okay, what does that graph look like and all this stuff. I don't want you to worry about that so much. Look at the identity. Tangent of x is the same as the sine of x over the cosine of x. So if you look at it that way, it's just like the previous example. When does the cosine of x equal 0? That's when you're going to have the vertical tangents, or vertical asymptotes. When the denominator equals 0. So we want to know, when does the cosine of x equal 0? That's all we want to know. And I always kind of do one of these, and if you think about your unit circle, this is 1, 0, 0, 1, negative 1, 0, 0, negative 1, and I think 0, pi over 2, pi, 3 pi over 2, 2 pi, and so on and so forth. So you can say cosine is my x value. It's when x equals pi over 2, 3 pi over 2, and so on, right? So we can just say it's for x equal to pi over 2 plus or minus, and we're going by pi's here. Pi k, or k pi. So that's where we're going to have our vertical asymptotes every time, and that's always what we're thinking. When is the function undefined? When is the denominator equal to 0? Okay, and behavior model. This is fun stuff. This sounds like a lot, but I'm going to show you the easy way to spell it. Write on behavior model for f. Let's say you've got this rational function, so you've got a function up here, you've got a function down here. As x approaches infinity, we want to know, how do we find this model? What is this going to be? Or negative infinity? Let's look at this huge, messy function. F of x, I'm going to write this out here. 3x to the fourth minus 2x cubed minus 3x squared minus 5x plus 6. We're going to put all of that over 3x to the fourth. There's a reason I wrote it like that. When numbers are small, folks, you put in a small number, you're going to get a change in the y value. As you put in larger and larger numbers, this fourth power, this highest power, is going to dominate. And none of this stuff is going to matter. So if you're looking for n behavior, all you're looking at is this right here. And when this equals 1, 3x to the fourth over 3x to the fourth, well, then the limit as x approaches and f of x approaches infinity is simply going to be 1. So we can look at that and we can simplify and see it. And I want to show you. I just happen to put this in my graph in my calculator also. So here's my function. And when you look at it from negative 10 to 10, you see all kinds of weird stuff happening. You look at the table, we're going to ask, and you can see big numbers as it's going to positive infinity, going to 1, as it's going to negative infinity, it's going to 1. Okay? Now, what if, let's come over here now again, what if you have something that isn't equal to 1? Well, I'm going to tell you the same thing. We're going to do the same thing. But what we have to do is make sure that these are in standard notation. Our exponents are in order. Well, in this case, yes, 2 is the highest here, 5 is the highest here. So since I want n behavior, I'm just going to look at this. Because all this stuff, when you get towards infinity or negative infinity, it doesn't matter. It just doesn't matter. So I'm going to look here, and I'm going to reduce that, and f of x, as it tends to positive infinity or negative infinity, is going to be 2/3 x to the 5 minus 2, x to the third power. There's your end behavior model. It's still increasing, so I would say the limit as x tended to infinity of f of x, well, as you put in bigger and bigger numbers here, it's going to go to infinity. Now, what if you put in smaller and smaller numbers? If I put in large negative, excuse me. So if I put in a large negative, because this is an odd power, I'm going to get a negative number here. So the limit as x approaches negative infinity is going to be 2/3 times a large negative number, or negative infinity. So as you're looking at your end behavior models, you want to be thinking about that. Now over here, this is another interesting case. We see we're in standard form, so I'm going to look at these, and my x cubes will cancel out. So actually in this case, what's left is 2/5. So the limit as x approaches infinity of g of x is just going to be 2/5. And you can put that into your calculator, verify that. If you put this in your calculator with your parentheses around the top, numerator and denominator, your division sign in between, plug in larger numbers, you're going to see you're going to settle into 0.4 or 2/5. So all you're doing, you're looking, cancel out what you can, and what's left is the limit. It's a constant, so that's going to actually, the limit as x goes to positive or negative infinity. This had a variable term in it. So you're going to have to put in very large numbers and very large negative numbers to see what's going on with that. So that's how we're going to do end behavior. So in summary, we can solve for limits using substitution, factoring, and the conjugate method. Nice videos on all three of these on the Moodle. We can look at limits graphically, look at large and small windows, We can use, find y equals b or b divided by 0, find our horizontal and vertical asymptotes. Remember, the horizontal ones are where you got y equals some number. The vertical ones are going to be where your denominator equals 0. We can use our table and ask for large and small numbers and find them that way. So this is a summary of what we're going to do, and again, use those other videos to see the details.